Greetings, stargazers, and welcome to section 21 on cosmology. So our goals for this section is to discuss the distribution of galaxies and matters throughout the entire universe. We're going to learn about these gigantic, large-scale structures that we have observed throughout the cosmos. And then we're going to start trying to figure out how they connect. And the key aspect is going to be the dark matter that we know exists, that's basically acting like a glue almost binding all these disparate galaxies together. Connected to that, we'll start talking about how the first galaxies, the first stars started to form in this early universe. And then we'll talk about some of the evidence for this expanding universe and the corresponding consequences due to how much matter and how much energy is present in the universe. So you know the drill, let's get our reading quiz out of the way. Let's ask ourselves, what does gravity do in terms of the expansion of the universe? The universe is blowing up in size. What does gravity do for that? And what does dark energy do for that expansion? Go ahead and pause, think about it for a moment, check your book. All right, and come on back. So what we'll say is that what gravity does, we know gravity has to slow down. It's one of these two. Take a apple, a ball, anything, toss it up, and what's going to happen? Well, gravity's going to grab that and pull it back down. Right? And it's doing that on a cosmic scale too. So no matter what, gravity is pulling things back. The expansion of the universe is being slowed down by gravity. Now, this dark energy, well, that turns out to be pushing the universe outward. So we know that as gravity slows things down, dark energy is somehow increasing the acceleration rate of the universe. So imagine there's a force that's pushing matter further and further out. Continuing in theme with our sections of going bigger and bigger, we're going to discuss these large structures, these cosmic expanding sizes. So let's get into galaxy clusters. And this is what we mean by clusters. We're saying look out there, and even though these things are separated by millions or billions of light years, in this case millions, right, they're going to be clustered together. Right? And you're looking at a picture here of what's called the Virgo cluster, one that is mostly a bunch of spiral galaxies, but we do see some elliptical galaxies too. And going to another picture of this, we can see kind of clusters here. There is a cluster of galaxies. Here's one loosely together. We're seeing cliques of clusters of galaxies throughout the cosmos. And so we can scan back, look even bigger and bigger view of the cosmos. And what trends do we start to see? What's out there? We start to notice these superclusters. Even nearby the Virgo cluster contains us, we notice here, and another, and another. So as we pull back, basically look at a wider view of the cosmos, we're seeing more and more of these joints. The bright spots are literal clusters of thousands of galaxies. Now, how we get these pictures are through what's called redshift surveys. We're saying, look at this galaxy, and as it recedes away, as we look through the cosmos, we notice that the entire universe is basically pulling away from us. And that's what we use the redshift. Remember, our Doppler shifts, as something goes away, it redshifts the light. So we look at all the cosmos, we see the redshift, we quantify, we measure the amount of redshift. And we start to create this map of the cosmos. And we see these patterns here. We're going to have these filament structures. By filament, think of these long threads. So we'll see a arch of galaxy clusters, another one. And then you'll find just voids, just empty space, where there's not a lot of literal galactic material there. So the conclusions that we've gotten to now is that, one, galaxies in the universe, they're not randomly distributed. Right? They're not just sprinkled throughout the cosmos randomly. They have clustered together. More than just the clusters, they're making these filaments. Each bright spot in this simulation picture here, each bright spot represents another cluster of galaxies. The brighter the spot, the larger the galaxy cluster. Right? And so these bands of galaxies are creating what we literally call, let's change that color. These are our filaments. Right? The sheets are a bit more broad, but our filaments are the lines here that you're seeing of bands of galaxy clusters together. So how we quantify these redshifts is, recall this from a previous lecture, our galactic redshift, it's this z quantity, this z parameter. That's a dimensionless number. We're saying, look at basically the scale of the Doppler shift. You say, what's the wavelength that we detect here on Earth? And we subtract the wavelength of what it'd be like if that thing was at rest relative to us. So to put that in perspective, what I mean by rest, imagine I have a spectrum tube, let's say neon gas. Hopefully everyone recognizes neon lights with that bright orange hue to it. So I take that neon light for my example here, and it's sitting right next to my face, relative, stationary to me, and I see that orangish glow. Now I put that on a rocket ship, and I send that neon gas flying away, and the light starts to shift. So the rest wavelength would be that orangish glow from my neon light, and then the observed wavelength is what I literally detect here as my neon bulb is on that rocket ship flying away from me. So this is a dimensionless quantity because we divide by the rest wavelength to basically scale and normalize things. Now let's talk about what the z means. We're seeing z shift in this image from 0 to a 0.14. What does that mean? So if you have a z shift of 0, it means that the observed wavelength minus the rest wavelength was 0. They're the same name. So that means that this is z0. That means this neon bulb is stationary relative to me. It's not moving. So the smaller the z value, the closer to 0 it is, the slower the object's moving. Now, if you start to increase, right? If I go to a z value of 0.1, that means that relative to me, the object that produced that light is moving somewhere close to 10% of the speed of light. This isn't one for one. We have, it's not like if this was 0.9, things would be moving 90% of the speed of light. It's not a linear equation like that in that regime. But for our purposes, a z of 0.1, that means that my neon light is on a rocket ship going about 10% the speed of light away from us. So you'll notice as you get further and further away from the cosmos, things are getting more and more redshifted. The further away it is, the greater the redshift, the faster the universe is expanding away from us. This is a key theme that we're going to keep coming back to in this section and the next one. The fact that as you get further away from us, as you increase the distance, the redshift is also increasing. The further away something is from us, the faster it is going away from us. The universe is expanding outwards and faster. So, let's start looking at little details here. We'll notice that between the galaxies, we'll find lots of hot gas observed. And think of those active galactic nuclei, the quasars, where you've got the supermassive black hole, the swirling material accreting around it, and as it's accreting, getting superheated and creating these giant, basically, bands of, could be anywhere from radio waves to X-rays being spit out of the center. So when we see these hot plumes of gas outside of the galaxies, most likely that was something that got ejected out by just some powerful cataclysmic event. Could have been a supernova too. That could do it. Right? And we look at those gases and we see heavy elements. So We know that these are star-forming regions that have had a long lifespan and started spitting out the heavy materials that the stars fuse together. Now, let's go back to our Milky Way. Yes, it is true. Across the cosmos, everything's expanding outwards. Let's zoom back in a little bit. Zoom in. We come back to our Milky Way, and we start seeing this cluster here. And this is what we've dubbed the Great Attractor. Something about the gravitational forces here are causing us to pull together. Remember how Andromeda is on a collision course with the Milky Way? On a local level, we have to be very careful about the size of the universe here. Yes, I just said the universe is blowing up in size, but that's on the universal scale. I'm going to shrink us back down to our cluster, our galaxy cluster, where there you can have gravitational interactions pulling things together again. Just like Andromeda's on a collision course with us, we see that the Milky Way, we're having this gravitational pull towards what's been dubbed the Great Attractor. And based on these interactions alone, that's led us to give us another tool to say, look, there's this mysterious substance that we have to call dark matter. Right? We observe these gravitational attractions between material. We don't see what's the source of the gravity, but we know there is a mass there because of how these things are moving together, how they're being gravitationally attracted. And that comes from the name. That's the name, the origin of dark matter. We see an effect of mass that is present there, but we don't see the mass. You can see other effects of dark matter by looking through galaxies, and you see this gravitational lensing, right? Specifically this one, you see this kind of lensing effect. You can almost make out as if there's a lens there, where suddenly the light is warped around the galaxy there. Right? This is distorted in pictures because of the supermassive objects that are present there. Remember, gravity distorts space-time, and light, without the distortion, would just go straight across. But with that distortion, the light will bend. The rays bend around massive objects. So that comes back to this guy again. We look at galaxies and we see this gravitational lensing effect. Now, stitch these two pictures on top of each other, and now we're starting to get a map. We take that X-ray image, stitch it on top of that visual, and we're starting to see basically this dark matter halo. We're seeing the presence of how the dark matter is there throughout all of that material. Still can't see it, but we know it has to be there. So here's a diagram, a schematic view of what I was just talking about. Right? So imagine we have this distant, faraway galaxy here, and we're the observers here on Earth. And as light from that galaxy is passing through the cosmos, say we had light rays coming like this, the presence of basically dark matter halo here and here and here, and the net effect ends up being just one big dark matter collection. There's dark matter spread amongst all of those galaxies, amongst all those cluster. Right? The cluster of galaxies and the dark matter that's present creates a gravitational lensing effect that close that one. It creates that lensing effect so that these rays that are traveling one direction bend with space-time and create those distorted view of the cosmos, that lensing effect. So, what is dark matter? Simply put, it's the missing matter in the universe. We've detected it before by looking at mass to light ratios in galaxies. We say, look at a galaxy and count up how much light we see and how much mass is there based on gravitational effects. An application of Kepler's laws again. And you notice that the rate these things are moving, the speed they're moving at, the amount of light does not match with how massive it is. It should be way more massive. Comes back to those rotational speeds of the galaxies. And now we've got these effects of this gravitational lensing of light being bent as it passes other galaxies in the foreground. And this combination means that the universe has to be way more massive. We don't see it. We can't see it. That's why we dub it dark matter. We haven't observed it, but we have detected it. We know it's out there. So, one last point. I like to bring this up here because I often get questions about this. So I really want to emphasize, dark matter and dark energy are distinct concepts. They are separate things. You don't just get to interplay dark matter, dark energy. They represent different physical consequences in the universe. All the name dark implies is we know it exists. We don't know what it is. That's all the dark refers to. All right. So do keep that in mind. Dark matter, dark energy, they're separate concepts. We will get to it in a later part of this section. Not this video, but a later one. All right. So, question I'll propose to you guys now. We're trying to figure out what this dark matter is. And we see how, because it's mass, it can bend light. But we do have some qualifying ideas. We don't know specifically what it is, but we know what properties it must have. And one property of dark matter we know it must have is that it has no electric charge. It must be neutral. So the question I propose to you is, how do we know that? I just told you, literally in the previous slide, we don't know what dark matter is. So how can I so confidently tell you that I know it must have no charge? No excess positive charge, no negative charge, and possibly just straight up no electric charge. How can I know that? Let's go ahead and pause, think about this for a moment, and come right back. Think back to way back in the beginning, section 5, where we talked about our first thorough investigation of light and its interaction with matter. We have a little picture here. Here's my little proton. Here's my proton. And let's give it an electron orbiting around it. So what happens if I was to shoot in a photon of the right wavelength? Boom. If I shoot in a photon of the correct wavelength, what ends up happening is that electron could, in the picture I'm going for, it could say, all right, you match an energy level I like, gobble that up. So let's see here. It's on, right. We gobble up that electron, or that photon, and we went from one energy level to another. So if you have charge, you interact with light. And if you want to go back down to the energy level, if you want to go from a high energy level back to a low energy level, what do? You spit out. You eject a photon to go down energy levels. So there is this immediate connection between having electric charge and your interactions with photons. Well, what's this thing about dark matter? It doesn't interact with light. The only way we've detected it is because of its gravitational mass, its gravitational effects on cosmos. But it doesn't produce its own light, it doesn't absorb light. Photons can pass right through whatever dark matter is, and that dark matter does not generate its own photons. So for those reasons, that's how we know that it can't have electric charge. Because if it did have a charge, even a tiny one, even a tiny charge, it would still interact with light and produce electromagnetic radiation. So, Yes, this is one of those mysteries of the cosmos. This is something that we know must exist. We can figure out some of its properties, but we still haven't figured out what it is. I'll tell you, me personally, I find this super exciting. So, what are some dark matter candidates? What are some things that we think might be dark matter? And this is an oversimplification, but we have basically two categories. We could have what we call machos or wimps. And the naming convention is meant to evoke what these objects could be. So let's go with the machos first. These could be called massive, compact halo objects. So we're thinking potentially just some small M-class stars, more likely Jupiter-sized planets, white dwarfs, neutrons, or even black holes. So basically you're looking for a very, very massive thing that's also compact on star sizes, right? So you're looking for a very heavy, compact object. And this meets some of our qualifications or some of our definitions of overall being electrically neutral, doesn't really interact with light, doesn't really produce enough light. And so the concept is you go into those galactic halos and it's just, look, there's a brown dwarf, there's a brown dwarf, there's a Jupiter-sized star, there's a black hole. And you just scatter enough of these machos throughout the area such that they don't really produce enough light for us to see them, or any light at all because of the black hole example. But they create the gravitational distortions to match with what we observe. The issue with machos is that we just haven't found enough of these to account for the sheer mass of the galaxies that we see. So while yes, there are probably a lot of macho objects out there, this probably, but qualifier, we don't know for them. But I'll say this probably isn't all the dark matter or the biggest source of matter that we see in the galaxies. So we have another idea. This one we call the WIMPs, and we call these weakly interacting massive particles. So remember our solar neutrinos? Every time fusion happens in the sun, those neutrinos, those get produced and just shoot straight out of the star. Well, those neutrinos have a certain amount of mass to them, and they don't really interact with the material. We have to wait a long time. Basically, we build giant water tanks deep underground and just hope that one of those neutrinos will ever so fortunately hit a water molecule. But in general, they don't. So that's where the weakly interacting term comes from. So in this model, we're saying, look, there's a new, basically fundamental particle of the universe that we don't know about because it doesn't interact with light, but it does have enough mass. And so basically we propose this base sea of these WIMP particles just floating out there. And that's creating the missing mass of the galaxies. And we have, like the Large Hadron Collider and ISS, trying to conduct experiments to detect these things. So this is our exploration of how to find out what the dark matter is.